And the next talk is from the same group, and this time on Scalable Taint Specification Inference with Big Code, and the talk is going to be given by Victor.
Hey everyone, my name is Victor. I'm here today to present our talk, which is a joint effort between Deep Code and SRI Lab of ETH Zurich. And after the previous talk, you probably figured out that we do research in the area of big code. That is, we train models on massive amounts of publicly available open source code in order to improve our results on some program analysis tasks. And today I'm going to present one of those systems that we used and that allowed us to increase the detection rate of security vulnerabilities by 30 times. But first, let me start with a bit of motivation. So the list you see on the slide is the so-called OWASP Top 10, which is an international standard of top 10 most dangerous security threats to modern web applications. And the 4 of them highlighted in bold are related to the so-called injection vulnerabilities. You probably all heard of them: SQL injection, cross-site scripting, path traversal, and so on. So those vulnerabilities enable attackers to inject malicious exploits into the application in order to compromise it and make it behave in unexpected ways. Let's take a closer look at how those vulnerabilities look like. And to this end, let's try to develop a small web application that would allow users to upload files to the web server. And let's see what can go wrong with this. So the application will work the following way. First of all, it will read the file name provided by the user. Second, it will concatenate the file name to some path to some upload directory where the files will be stored. And third, it will save the file to the obtained path. So what could possibly go wrong? Well, many things. If an attacker provides a malicious exploit that contains a ... sequence, then the attacker will get the ability to overwrite arbitrary files on the server. For example, the etc passvd in this case. And this pattern, when the attacker provides some untrusted input, which then falls into a critical from the security point of view function, is common to all injection vulnerabilities. And there's a very natural and popular technique to detect such vulnerabilities. It's called Taint Analysis. Taint Analysis works by constructing and inspecting the graph, the data flow in a program, which can be nicely visualized with the graph that you can see on the right. And this graph has a couple of special nodes in it. So first category of special nodes are the so-called sources, which correspond to untrusted input. In this case, for example, the file name. And I'll use the blue color for sources throughout the presentation. The second category are sinks. Sinks correspond to critical from the security point of view functions, and they'll be highlighted with red. And Taint Analysis gives us a very nice model of a vulnerability. So basically, a vulnerability is a path from a source to a sink. So how do people usually fix such vulnerabilities? Well, most of the time, the most trivial fix is to insert a sanitizer, which basically takes the untrusted user input, somehow cleans it, and makes it safe to be used with the sink. And now if we take into account the sanitizers, the vulnerability model becomes, so basically a vulnerability is a path from a source to a sink that does not go through a sanitizer. So as you can see, the Taint Analysis, well, at least conceptually, is quite straightforward, but there's one big caveat. It relies on manually provided specification of sources, sinks, and sanitizers. So Taint Analyzer has to know in advance which nodes are sources, sinks, and sanitizers to work. And the performance of a Taint Analyzer very highly depends on the completeness of the taint specification. So whenever it misses a source or a sink, this will result in undetected vulnerabilities. Whenever it misses a sanitizer, this will result in false positive reports. So the bad news here is that creating taint specification is a big problem. It requires a lot of labor. There are many different programming languages in which web development is done. And in each of the languages, there is many different frameworks, and each of the frameworks has hundreds of different APIs. And those frameworks, they just keep appearing and appearing. And in the end, this results in a tremendous workload for anyone who wants to maintain a sane taint specification. So we faced this problem at Deep Code when we were working on our security analysis, and we decided to solve it by automatically learning taint specifications from Big Code. And our setup looked the following way. So we had a huge training corpus of open source projects from GitHub. We had a static analysis that would basically give us a data flow graph for each of those programs. We had a small set of known specifications. And what we missed was a system that would combine those inputs and give us a bigger and more complete set of automatically inferred specifications. The requirements for the system were very simple. So first of all, since we have a large training set, it should be fast enough to scale on big code. And second, the system, since we didn't have that many specifications, the system had to work fine with just few known specifications. We looked at previous work, and we found two papers that did similar things. First of them is Merlin. Merlin is a system for semi-supervised learning of Taint specifications. But unfortunately, its inference is based on factor graphs, which, as we found in practice, would not scale for big code. Second system is SUSY, which has a similar goal. It's a system that uses support vector machine model to detect new sources and sinks for Android privacy leaks. But as you might guess, since it uses SVM, it requires a lot of supervision to work. So yeah, this is the story of how our system called Seldon came to be. The key insight of Seldon is a novel inference algorithm based on linear constraints that makes it fast enough to work with big code. And now, since we can process huge amounts of training data, we can slightly lower the requirement on how much labeled data do we need. So this enables us to use semi-supervised learning to infer new candidates. Okay, so now let's go step by step over some of the components of the system. First component is the static code analysis. There's no magic going on here. It's quite standard. We use a static analysis that would basically, for a given program, give us the data flow graph for this program. Nodes in the graph they correspond to events in the program, for example, function calls or parameter loads, and so on. And edges represent the data flow relationship between events. Yes, and the analysis relies on the flow context and field-sensitive points to analysis. The second component is a set of 3 beliefs that we use. We assume that those beliefs should hold almost everywhere for almost all training programs. And we use them to derive constraints on the inferred candidates. So the first belief is basically a rephrasal of the goal of a sanitizer in the program. It says that whenever we see a sanitizer that protects a sink, it means that there should be a source that the sanitizer is protecting the sink against. The second one says that vulnerabilities do not occur often. This means that basically most of the paths in the program are sanitized. So whenever we see a source falling into a sink, there's a very good chance that in between them there's a sanitizer. And the third belief is basically a mirrored version of the first one. It says that whenever we see a source that falls into a sanitizer, most probably the sanitizer is used to protect some sink. So there should also be a sink somewhere in the program. So the important thing to understand here is that those beliefs are not axioms. We do not expect them to hold everywhere. But we do expect them to hold often enough so we can use them to derive new constraints on the inferred candidates. So yeah, let's see how we do this, how we instantiate the beliefs on the actual data to derive constraints. So first thing we do, we assign 3 scores to every candidate, to every node in the Taint graph. The score of it being a source, a sanitizer, and a sink. All the scores are between 0 and 1, where 0 means definitely not, 1 means definitely yes. Important thing here is that if 2 nodes are basically, they refer to the same events, and for example, if they refer to the same function, to a function call to the same function in different places, we will map them to the same scores. And yeah, let's see how instantiate, for example, the first belief. So just to recap, the belief says that if there is a sanitizer falling into a sink, there should also be a source falling into the sanitizer. So if we rephrase it a bit, it might sound like this. If B is a sanitizer and C is a sink, then at least one of the candidate sources XYZ falling into the sanitizer has to be true. And now comes the main insight of the paper. This constraint can be nicely expressed with this linear inequation. So, for example, in the case where B is a highly confident sanitizer and C is a highly confident sink, then the right part will have a big score. And in order for this constraint to hold, the left part has to have a big score as well. So at least one of the sources on the left side will get a big score. On the other hand, if we're not confident about the sanitizer or the sink or both, then the right side will be small, and there's nothing to do for this equation to hold it. It will hold by default. Yeah, so this is the constraint we collect for the first belief. Similarly, there's this very similar constraint for the second belief, for the third. Now what we do, we take all the data flow graphs in the training set, we collect all of those three constraints for them, we combine them into one global constraint system. Then we add hard constraints for the known specifications, and this is quite straightforward. Whenever we have a source in the known specification, we require its source score to be 1, and the sanitizer and the sink scores to be 0. And we do the same for sanitizers and for sinks. Yes, and in the end, when we obtain this big system of linear constraints, all we have to do is feed it into a linear optimizer that would give us a solution, and then we can map the solution to newly inferred specifications. So we developed the system for the three languages, for Java, JavaScript, and Python, and it's running live on deepcode.ai. But today I'm going to present only the Python version, since it's the version described in the paper, and I'm going to give you some statistics about it. So the training dataset we used contained roughly 45,000 of files from web-related projects on GitHub. The set of known specifications was small. It's only 106 specifications. We obtained the constraint system, which had around 211,000 candidates and 505,000 constraints. And out of all this, we got roughly 7,000 new inferred specifications with the expected precision of 2/3. So basically, out of 106 initial specifications, we expanded the set to around 4,500 true new specifications, which is a huge recall boost. The key characteristic of the system that made this possible, that made learning from big code possible, is the speed of the system. So you can see that the learning time scales linearly with the number of files we use to train. So for the biggest data set of 800,000 files, it took us around 4.5 hours to train, which is a feasible time. So besides benchmarking, we did a couple of other experiments. First of all, we checked if learning from big code is actually more useful than learning from an individual project separately. And to this end, we sampled 3 projects from the training set. We trained the model individually for each of the projects in isolation. And then we compared the performance of this model against the performance of the big model trained on big code. And it turns out that learning from big code is beneficial for both precision and recall, which is nice. Second, we checked how many new security vulnerabilities can we predict using the inferred specifications. So it turns out that the recall increased 30 times. And the precision stayed more or less the same, which might sound a bit surprising, but when we took a closer look to it, we observed that the seed specification misses a lot of sanitizers, and this results in 40% false positive rate. On the other hand, the inferred specification is more complete in terms of sanitizer, but it also has, due to misprediction, it has false sources and sinks. Another interesting thing to notice here is that a big chunk of the false positives, the yellow one, is not related to Taint specifications at all. Next thing we did is we checked if our predictions are actually useful for real-world projects. To this end, we found and reported 49 severe vulnerabilities in 17 projects from GitHub. And an interesting thing here is that only 3 of those vulnerabilities could be detected using the seed specifications. And another thing is that we tried other tools, and none of them was able to detect any of those vulnerabilities. So we speculate that the other tools could also benefit from our method of learning specifications. Yeah, so to conclude, today I presented a system, a semi-supervised system for inferring taint specifications from open source code. The key insight, the key novelty of the system is the formulation of taint specification inference as a linear optimization process. And the system runs online on deepcode.ai, so everyone is more than welcome to go and try it. Yep. Thank you for your attention. I'm ready to take questions.
So, time for questions. Maybe let me start with one. So one of the assumptions is the second belief that there usually is a sanitizer in between a source and a sink. So while thinking about a related problem for JavaScript, we found that this assumption, at least for the packages in JavaScript that we looked at, is usually not true. So you find many examples where you have where data just flows from a source to a sink and there is no sanitizer in between. So my question is how many violations of this second belief could your system tolerate? Did you measure this by maybe disturbing this belief a little bit and seeing how well it still works?
No, we didn't measure it, but so basically we selected the training set in such a way that hopefully the code is good. So we selected projects from GitHub that have lots of stars and hopefully are mature enough. So yeah, we assume that this holds for those projects.
Paddy Krishnan from Oracle Labs. Very interesting talk, thank you. I just had one question. You rely on static analysis to produce the data flow facts. How sophisticated is that?
The analysis?
Yep.
I would say it's pretty standard. So it's
like for example, for Python, how many of the dynamic aspects are you able to resolve, or can they be left unresolved?
So it's field sensitive, so it propagates taint through fields. It over-approximates the standard Python collections, like dictionaries, lists, sets, and so on. What else? It's aware of named arguments, and for example, when you pass the star key value arguments. Yeah.
Okay, thank you.
We still have some time. If anyone has a question, go ahead. Otherwise, I can ask another one. So another assumption you have is that every function, so basically that a function is a source, a sink, or a sanitizer, no matter what arguments you pass into it. Did you see violations of these assumptions? Like,
yes.
For example, you could imagine a sanitizer that only sanitizes paths if you pass some other argument telling it to actually sanitize paths. Did you see such cases?
Yes, and this was a big reason for like lots of false positives, but I would a bit rephrase it. So we saw a lot of mispredictions related to sinks. So imagine you do a SQL query with prepared statements, and first is the string, and the second are the arguments. So basically only the first argument is vulnerable, and the second and third are not. So yes, due to this, we observed a bunch of, not a bunch, like lots of false positives.
Hi, this was a really cool talk. I saw that you handle Java now, and I'm wondering if you run into any issues with apps that use these big hairy frameworks like Spring, because there a lot of the data flow is due to magic defined in other configuration files. So it's not that there's a source call or method from a library that returns you tainted data, is that the framework magically passes in tainted data into one of your own methods. So were you able to extend this technique to handle that, or does it handle it already?
No, I give up. So those steps are usually...
That's what I did too.
Yeah. There's indeed some declarative magic going on when you define things in XMLs, and yeah, this complicates the analysis a lot. And no, I didn't do anything.
Okay, thank you.
Thank you.